And was packed with a lot of new information and concepts. I particularly like that picture of Mars that you showed that was assembled by converting the Mariner 4 digital image into a hand color-coded image. And that was really fascinating. These are bits and pieces we don't know, and we have to listen to a lot of talks like these to get all these like minute details which put the fun into the game. And moving on to the questions. So first and foremost, how do you think this new finding of yours, like it alters the picture of habitability we have? Does it paint a new picture on Mars?
It does, but I would like to impress this point that oxygen was not present on Earth when origin of life happened on Earth. So when life started on Earth, it was anaerobic life. When oxygen actually started coming out, it was actually a mass extinction event. So oxygen actually killed a lot of organisms at one point of time. So, I mean, if Mars did not have oxygen at one point of time, it doesn't matter. Life finds a way to thrive, right? So things can happen, but yeah, I firmly believe that it was not oxygen that might have played a role on Mars.
You were mentioning about shadow region on the lunar poles. So, in terms of doing the mineralogy and composition analysis, so most of the cases we are using hyperspectral sensor data or basically an optical instrument. So what are the chances to use these instruments to get a near about or probable compositions from these areas? Because these areas are mostly under the shadow for near about all the time. So what can we do to get the mineralogy derive the mineralogy from these particular regions?
That can be complemented with radar data, and these information can be used in association with the hyperspectral data and the permanent shadow region, and those regions nearby, they can be utilized for understanding the compositional variation. If the hydration features would have been present, maybe in the form of frost ice, so they may be in the adjoining regions also. So you have to map them, you can quantify them, then you can use the subsurface data, radar data for ascertaining so whether what ice is present, so what type, whether it is there or not.
So, hello everyone. Am I audible? I think. I'm a pure person again, and I am one of the co-founder and director of IIREES. Today, Dr. Narayan Bose and I will be your host. Dr. Bose is a structural geologist currently working in the oil and gas sector. He is a mentor of IIREES and a convener of this EPS3 event. As you know, IIREES is an India-based educational and research initiative that aims to build a new generation of creative, passionate, and critical thinking natural scientists through transformative education and research support. Earth and Planetary Science Seminar Series, that is EPS3, comes under one of our core activity. So far, we have organized 2 lectures on planetary sciences and related topics. I hope you enjoyed both the seminars. If you somehow missed those seminars, then you can just visit our YouTube channel and watch the recorded sessions. Today, we are delighted to have Dr. Urmi Ghosh, a digital mineralogist from James Hutton Institute, Scotland, as our esteemed guest speaker. She will be presenting on a super exciting topic, that is why should we learn the machine learning and its geoscience applications, tool for geochemists. I'm welcoming her also. So far, we have received a fantastic response from all across the globe. On behalf of IREES team, I thank you everyone. If you have any questions, please feel free to write us in the chat box during the seminar or after the seminar. And please turn off your videos and microphone during the presentation. And during this presentation, we will share a registration form. That's Google form. Those who are interested to get certificate, you can just fill it up and send. Okay. Now, without wasting much time, I would like to invite Dr. Bose to start hosting the session. So thanks for joining us today.
Hello. Am I audible, Priyabrata?
Yes.
Okay, thank you. Thank you, Priyabrata, for the nice introduction.
Thanks.
Okay, I think Urmi is also present here. Hello, Urmi. Are you there?
Yes, I'm here. Yeah.
Okay, nice. Nice to hear from you. So, all the participants, welcome. Good morning, good evening, good afternoon from the wherever on the globe you are. So, today we have Dr. Urmi Ghosh. She is going to share her experiences on machine learning, and I am quite sure that it will be a very nice experience for us to listen from her. Dr. Urmi Ghosh did her BSc from Presidency University, Kolkata in 2014. After that, she did MSc from Indian Institute of Technology, Bhubaneswar, and she received her MSc degree in 2016. After that, she pursued her PhD in Indian Institute of Technology, Kharagpur, under the supervision of Professor Devashish Upadhyay. And in her PhD, she worked on orogenic processes with the help of trace elements and isotope geochemistry. So a part of that we are going to see just now. And after receiving her degree in 2022, she was affiliated to Zhejiang University of China for a short duration. And after that, she is now in her current position, which is as a digital mineralogist in the prestigious James Hutton Institute. So without a further ado, I am now going to hand over the stage to Urmi. Everyone, please welcome Dr. Urmi Ghosh.
Thank you, Dr. Narayan Bose, for the kind words, and I would like to thank IIREES for giving me an opportunity to share my research and my experience. So I'll start sharing my screen.
Yeah, please.
So is my screen visible?
Yeah, it's visible. Please start.
Yeah, thank you. So the question is, why should we learn machine learning as a geochemist? So I am a geochemist before learning machine learning. So why should we as a geochemist learn machine learning? So that is what is the main topic of my discussion today. So I am actually here to give you a brief overview of why should you learn it. I am not a statistician or I'm not a programmer, so that I'll give you the basics, but I'll let you know why this has become very relevant tool for geochemists as well. So I'll just give the outline of my presentation. So I'll start with what machine learning is and how they are generally being applied in our everyday life. So how recently in geochemistry it has found its application, and a small case study from my own research. So first, starting with what is machine learning. So obviously we know learning is any process by which with experience and with repeated performing the same task, we improve our performance. So when you teach the same to a machine, that is called machine learning. So for example, if you have a task T and you repeat the number of performances, then the experience will improve. That is, the E will improve with increasing number of P. So for example, there have been multiple chess play between machine and the Grand Slam players. So in the initial stage, when there were such matches, the machine would actually lose most of the time. Then came a time when the games would almost every time end in a draw. But with the experience the machine was gaining, finally it could beat the world champion at a stage. So we do not expect the algorithms to be perfect at the initial stage, but when you provide more data to the machine and like it repeats the like task again and again, and with obviously it needs a number of data points, like if you increase the number of data points, it will be training on a larger data set and then it will improve its performance. So these are three terms which you often come across, like artificial intelligence, machine learning, and deep learning. So they are like it's sometimes difficult to distinguish between them. But like artificial intelligence is anything that is you teach a machine to be smart. So in case of machine learning, you actually give a data set and train it like again and again to be perfect. Whereas in deep learning, it would require a huge, like a larger amount of data set, and we would and it has a very complicated structure, and we would expect the machine to learn by itself. Like it is kind of a like complex neural network method, whereas in machine learning, we try to train them methodically. So in case of traditional programming, what we expect is we provide the computer with the data and we give it a program, and then finally we expect an output from from the computer. But in case of machine learning, we are not going to give them a like algorithm or which way to perform the job. We are going to train it with data and output. So and depending on the different algorithms, it is going to fit the output to the data. So in our everyday life, of course, you have seen machine learning applications and you have used them. So maybe we don't know how it works or like the complex algorithm behind it or the huge amount of codes that goes behind this. But we obviously have experienced and we have used these applications. So in our everyday life, we use face detection. Like obviously in even in mobiles, we have detection app, the Google Lens feature. So they are basically image recognition. So it also has a very important application. For example, like different like X-rays, or in case of medical field, the images, suppose the X-ray plate. So that often machine helps in detecting if the X-ray is cancerous or not, if there is like some if there is some problem in the internal organs or not. So often the initial image recognition is done by an instrument. In case of speech recognition, the voice search Google has, so you know them, like automatic cars, junk email detection, movie recommendations, or prediction of stock markets. So these are all different applications of machine learning. And in every case, the precision increases with the number of time the machine performs the task. For example, in case of automatic cars, for every kilometer the car runs, it gathers data. So how the road is, like what kind, like how it should like learn to drive. Of course, there are manual input from actual drivers, but even when it runs, it collects the data from its surrounding. So normally, what are the different types of machine learning? So we can broadly classify it into 4 types: supervised, unsupervised, semi-supervised, or reinforced. I would not discuss in details to that because there are enough materials online, so you can find it if you're interested. I would mostly focus on what we need to study, like application in geoscience. So in case of supervised learning, the main thing is there is a predefined outcome. For example, if we are trained, we need to give a predefined output to the algorithm. Just in this image, what we can see is we are feeding this the machine with images of different fruits. Now we can feed it with images of different like cats or dogs as well, so different animals, and by these are the input data. So these data are labeled, so every image that has a label, like what kind of image it is, like is it apple or is it orange, so the algorithm knows what in which cluster it has to fit it. So this, and in the output you expect them to correctly classify it. But so this can be of 2 types. So this is a classification problem I'm talking about. So similarly, it can be a regression problem as well. So these are the common algorithms that are used in classification and regression. So there are simple models such as logistic regression or linear regression. However, as the algorithms can get complex. So it depends on our requirement, like which algorithm we need for our expected output. So depending on that, we choose it. So if you consider in case of a geochemical problem, so suppose there are several geothermometers or geobarometers, and often they are trained for a particular temperature pressure range, or a very small amount of data set. So the thermometer that work on some similar kind of data set that might not work if you change the nature of the data set. So if you increase the data, like the input data, so if we that might give you a universal thermobarometer. So for example, there have been recent work based on garnet composition. So the garnet composition ultimately helps you in finding out a consistent thermometer that works for a larger range. In case of classifications as well, you can find that based on composition of a mineral, for example, like biotite composition, or for example, you can consider whole rock of basalt. So based on that composition, you can actually classify into different tectonic settings, from which setting the particular rock is coming from. So these are some applications that you find in geosciences. In case of unsupervised, you do not have a label attached to the inputs. For example, you are giving a large amount of data set to the machine, and you're asking them to just classify, like just find the clusters, or just find how many different type of samples are there. So here in this image, you expect the outputs of dogs and cats to be separate, but you won't get a label. Like it won't separate out what exactly which kind it is, because when you're inputting the data, you input them as a whole. You do not label each sample as cat or dog. So in case of clustering, you would expect the same. For example, you input a large amount of chemical data set, and you expect the computer to classify into 3 or 4 clusters, and based on like the number of clusters, you would of course choose, like you want 3 clusters or 4 clusters, and it would, based on the differences in chemical composition, it would cluster. And of course there are different algorithms for that as well. So why would we use machine learning? So one thing you must be aware of, that not every problem requires machine learning. So you, for example, if you try to if you are trying to build a thermometer, it's okay. Now a barometer, you can try machine learning. But suppose you have a very 15 points. So you are taking 1 garnet and 15 data points. You cannot expect to run a machine learning on that kind of problem, because you, first of all, you do not have that amount of data set. Second of all, you do not have a problem that requires machine learning. So you can only for 15 point, only for simple problems. For example, if you want to calculate something that can be easily done by addition, subtraction, multiplications, like normal easy problems. So of course, machine learning would give you a linear regression as well, but that would be wasting your resources. So you have to find out if your machine, your problem requires machine learning. And mainly it is used on areas where human expertise does not exist, or you cannot you have an understanding what it might be, but you cannot exactly do the problem yourself. For example, you might have a very large data set, like 40,000, 50,000 data points. You cannot actually take them to Excel and you cannot manually plot them, or in other sense, you cannot visualize them. For example, we can plot up to 3-dimensional diagrams. So if we have 24 columns, we cannot actually plot them, we cannot visualize, and so in that case, it would be easy for a machine to deal with that kind of data. So first of all, that is the thing. You need to identify if your problem needs machine learning. Do you have enough data to train your model? Also, your precision would increase if you increase the amount of data. And if you increase the variety of data, like different types of data, your model will be more universal. And you have to understand that only what kind of data you train in, you can expect to get an output only in similar range. For example, if you're training a model in a lower temperature pressure range, you cannot expect to extrapolate it to a higher temperature pressure range. That won't work. Like in most cases, that won't work because it's not always linear relationship. And you must be very careful about what kind of data you're putting in. So if you're putting garbage in, the data in, you cannot expect a good output. Even a very good model would not fit bad quality data. So you would need to find what is the right algorithm for the job. If you are getting a good fit in a simpler, simple model, for example, if in a linear regression or polynomial regression, you're getting a good fit. If you increase the complexity of the model, there is a higher chance that it will overfit. And of course, you have to be careful that you're overfitting your data or you're underfitting your data. So also which model to choose, you have to be careful, like how important it is for you to interpret the data. For example, you might get a very good fit, like a very powerful model, but in many cases, in case of complex models, such as in case of deep learning, it is a black box. So you don't know which are the elements or which are the main factors that are influencing your data, like influencing your output. For example, if you ran a deep learning algorithm, a very complex one, you're getting very accurate pressure temperature condition, but you have no idea which composition or which elemental abundance is actually affecting that prediction. So, and in case of simple like linear regression model, you would get a equation, like a proper equation. So, but often we go with a medium, like a middle ground, so that it neither overfits nor underfits, and you can interpret the model. For example, in case of random forest regression, you would expect to get a feature importance. So it will tell which factors have been important in calculating the output. So often we go with the middle ground. So that is you as a geoscientist to decide, or a geologist or geochemist to decide what is important for your model, what would you want as your output, and like how much interpretability will you want. So therefore, the domain knowledge is very important. Like these are the cases where the domain knowledge becomes very important. For example, if I take an example, like you're dealing with a database where you're trying to predict the salary of the employee of a company. But ultimately, after running the model, what you get is that there is a clear relation between the shoe size of the people and the salary of the people. Now, the model is showing it. You cannot do anything about it because it is simply statistics. Now, you will not believe the data or believe the output because clearly there cannot be a relationship between the shoe size and your salary. But if you're aware of the situation, maybe you'll realize that, okay, that might indicate that there is a gender disparity. And because the shoe size of female are generally smaller than the males, so therefore it is that gender disparity which is being shown in such a weird relationship. So instead, what you'll do is you'll try to input the gender of the employees and remove the shoe size. So therefore, therefore you should be aware of the situation, or what are the parameters that can actually work and what won't work. So therefore, domain knowledge is very important in case of any machine learning model. So a statistician would not be able to interpret a geological data how a geologist would predict better. So therefore, domain knowledge is very important because only 10% of the time you would actually run the model, and 90% of the time it will be just data cleaning and data analysis and interpretation. So normally, if we look at a machine learning workflow, this is a common machine learning workflow. So first, you'll build a database. So in case of geochemical databases, there are currently available databases for mostly for igneous rocks. In GeoRock and in EarthChem, you would have some compiled databases. And I'm not sure about the sedimentary rock because I haven't dealt with it. The soil and water geochemical databases are also there, but I think like the GeoRock for igneous rocks, that is and metamorphic rocks, that is pretty well compiled. And you can use other databases that other authors have already compiled. Or if you have a particular problem that you want to work on and there are no available databases, you have to compile them yourself. Now, if you're using someone else's database, you need to be very careful because somebody has compiled, like for example, in case of GeoRock, many times the students compile the database, and obviously they are prone to manual errors. So you would see that in case of Garnet totals you expect to be at least greater than 96%. But if you find a data which has a whole major element total approx 70%, you would be like you have to be cautious because that is not a Garnet data. That is possibly that might be weathered Garnet, or it has there has been some problem with that particular analysis. So you have to filter your data and clean your data before you actually use your data. And so that data cleaning is very rigorous. There are several algorithms for it. You can plot several ways and find the outliers. So I would not discuss that, but that is something you must be very aware of. And there will be missing data. A lot of data will be missing. So how to deal with the missing data? You cannot just put 0 in any missing data because that will be erroneous. So how to deal with that? What kind of techniques you can use? So that is a different thing actually. So you have to be aware of that as well. So you have to learn that. And after you have a clean amount of data, you have to do exploratory data analysis. So you have to make several plots. You have to find relationships. Initially, you have to have an idea what kind of data you are dealing with. What are the possible directions that your data can indicate? So what are the things your data can indicate? So that exploratory data analysis part is very important. Then you do sampling. Because of course, for example, if you have taken for example, tectonic settings, so you have different kind of samples from different kind of settings. So maybe 50% of your sample comes from subduction zone. So like if you in case if you're sampling, so you need to be uniform. You need to sample uniformly from every set of data, like every different kind of data that you have. Otherwise, it will be biased to a particular data, like a particular end part, obviously it will be biased to one particular type of sample. So therefore, different sampling methods are there. So you need to be aware of the different sampling methods, which sampling method will work for your data. And you can combine different sampling methods. You can break your total data set into multiple sets, and then you can individually sample from them. Because when you're training a data, like a machine learning model, you would need at least 60 to 70% of the data as a training data. So you would train the model with that data, and after training the model, you would test it with the rest of the data so that you can validate your model actually works or not. So therefore, these techniques are also very important, and they are as important as the model itself. So after that, you start your training your model based on machine learning algorithms. So as I named a few algorithms, so you can what kind of problem you're dealing with. That will based on that you will decide what kind of model you'll build. Then you can tune your model, so varying different parameters like till how many steps it will run, or how many combinations it will take. So based on that, you will tune your models so that the accuracy of your model can increase. And finally, you'll visualize your output and see the future importance and try to interpret your data. So I hope you have had a little bit of idea that what machine learning is about and how in geochemistry you can use them. It is not only learning the models. Yeah, of course, you will have to learn the machine learning algorithms, and that is a complex thing in itself. But apart from that, you must be cautious of everything in the geochemistry domain as well. So the data set itself. Now, a different if you look. Just search machine learning and geochemistry in Google, you'll come across a large number of papers. So recently, a lot of work is being done. So here you can see some of the supervised classification problems where the tectonic settings have been used, like discrimination of tectonic setting is done based on major element chemistry. So again, based on these major element chemistry, they have tried to predict if there has been a mantle metasomatism or not. And they are used to classify the different fertility of art magmas. So these are the different examples. So even in like regression models, and most common regression problems are like predicting the thermobarometer, like create a barometer, like thermobarometry and chemometry, and of course estimation of different elements. For example, lithium cannot be measured by normal EPMA, like electron probe measurements. So it has to be done by LAICPMS or some other like sophisticated instruments. So therefore, recently they have come, machine learning models have come up where you only using the major element composition you can predict lithium. Again, Fe3 plus, like which it doesn't classify between Fe3 plus or Fe2 plus. So that Fe3 plus Fe2 plus ratio cannot often be predicted based on their atom like APFU value. So therefore, like therefore, machine learning models like are already helping to predict the Fe3 plus values based on the major element composition. So these are some of the problems that are being solved by machine learning models in geochemistry. So to give an how it works, I'll just show a small case study, which is based on my PhD problem. So initially, my PhD was not anything on machine learning of that sort. So it was basically on ore geochemistry. So I was dealing with ore mineralization at tungsten delts of India, and and because my study was mainly funded by Indian Institute of Technology Kharagpur and CSIR. So like fellowship was funded by CSIR. So I would like to acknowledge them for this study. So basically, this is my PhD was focused on three of these locations, but I would only focus in like to give this case study overview. I would just discuss a little about this Belka Pahar region. It is the largest wollastonite mine in India, and these are the geological maps of that region. Here you can see that the pegmatite is intruding into the calcilicate rocks, and these are some of the samples that I collected from the field. Now, I was mainly looking at the hydrothermal alteration in these calcilicate rocks. So one of the main minerals in these calcilicate rocks was garnet. Now, these garnets are quite different to the like garnets you see in normal igneous rocks, or in case of metamorphic rocks. In case of metamorphic or igneous rocks in general, if it is not very calcium rich, you would find pyro or almandine kind of garnet, sometimes spessartine. Grossular maybe, but this calcium rich garnets, they are not very common in case of igneous or metamorphic rocks. So because this is a calcilicate rock, and in most of the skarn settings, they are very common. So you because of the calcium rich protolith, you get these calcium rich garnets. So mainly the samples that I dealt with, they belong to this grossular andradite series. So here you would find this grossular andradite series. This is the main type like garnets that I dealt with. So here you can see, so like when I was studying other minerals as well, so along with that, what I found is like garnet is readily reacting with any change in the fluid composition. So here I have found different generations of garnet as well, as I have mentioned. But what I am trying to focus on, like I want you to look at, is like how you can see these fine zones in these garnet, and it suggests that the nature of the fluid is constantly evolving, and therefore the garnet is readily responding to the change in the fluid, and as a result its composition is reflecting the nature of the fluid change. So these are the X-ray elemental maps, and they are mainly done on EPMA, electron probe microanalyzer. And these profiles are actually point analysis. So for example, this profile is along this direction in this garnet. So a large number of point analysis have been done, and then I have plotted them. So here we can see that this X-ray elemental images, like this change in composition is also reflected in this profile. So from here, after that, what I did is I did the trace elemental study. So even in when you look at the trace element composition, what you see is the garnet composition is the change in the garnet composition is also reflected in the trace elements. Like not only the major element composition is changing, but the trace element composition is changing as well. And for different elements, it is changing, and similar kind of garnets, you can see that there are there are several clusters. So similar kind of garnets, they cluster together, others they'll deviate. So even from a same location, with the small change in the your environment, the garnet is readily reacting to it. And based on that, I tried to construct how the fluid alteration has actually taken place, how the garnet evolved, and based on that, I gave I reconstructed the alteration, exoscan alteration, and the fluid evolution. But this also gave me an idea that because garnets are very sensitive, so they can actually be used to understand how, like, the O-type association. So in many worldwide, there are a large number of skarns which hosts economic deposits. So different kind of ore deposits are associated with these skarns, and people have tried to create bivariate plots, triangular diagrams to understand which kind of garnets have a ore association, which kind of ore association. But this could be done on a larger scale using machine learning. So that is what came to my mind while working on it. So for that, what I did is I prepared a data set, because when I started working, there was no pre-compiled data set for this particular problem. So I had to compile a data set. And obviously I mentioned that you must be very careful about compiling the data sets. So only the major element compositions of garnet were measured by EPMA, and I took only trace element composition measured by ICPMS. That also laser ablated, spot analysis. So after that, I cleaned the data. I would not go into details of cleaning the data, because that is entirely different topic in itself. So that will consume much of the time. So initially what I did is I tried to plot the garnet composition on the traditional classification methods that were already available at that time. So these are the main triangular diagram, and this is the bivariate plots. But you can see that when I am using all my data set, there is no clear distinction. Often these clusters, they are overlapping, and they it is not a very good classifier. These plots do not classify them very well. So first I tried to explore the data, as I mentioned. So that is very important. So what you see here are the correlation coefficients. So, and here are some of the bivariate plots have been plotted. So there was nothing surprising in this. They showed the similar kind of relation that I expected these kind of garnets to have. For example, these positive correlations between the LREs and HREs, that is very expected in case of garnets. So the LREs behave similarly and the HREs behave similarly. So there was no surprises there. And in this kind of garnet, in grossular andradite series, the iron and aluminium, the main interchange happens between this. So there was no surprise as well. But you can do one, there can be if there is some outlier or some weird value, that will be very evident here. In these bivariate plots, you would find some outliers that would indicate you that these points do not belong here. So it can be an efficient data cleaning technique as well. So here there were no surprises. So what I did is I plotted the garnet principal component analysis plot. Now, principal component analysis is an unsupervised machine learning technique where you do not tell the machine that they have to classify it. I just want the machine to look at the highest variation in samples and just plot them. This principal component direction 1, that would try to that will show the direction of maximum variation in composition. So in this kind of plot, what we see is it does not classify very efficiently. In case of major element, what you see is the classification is almost not there. Most of the samples, they overlap with each other. There is no clear clustering. So major element So major element composition might not be a very good indicator or a very good proxy. In case of trace elements, what we see is that certain groups, they can be identified. For example, this gold copper iron cluster, that is clearly distinct from the iron, like the tungsten molybdenum cluster, tin tungsten. But so therefore, PCA can be used to certain extent, but this unsupervised clustering might not work. So we need to go for something supervised, something more that we have more control on. And here in this plot, you can actually see the direction of the elements. So these, for example, these gold and copper deposits, they have enriched concentration of these elements, like they are LRE enriched. So they can give you an idea like how your data is behaving, like which elements are enriched, and how this direction of the different principal components, they can be indicated by these vectors. So for now, we need to move to a supervised supervised kind of classification. So for that, what I did is I divided the data set into multiple clusters. So this clustering was done based on k-means clustering. So you can classify it into how many different data that sets you want. So you can choose the k-means to be 3 or 4, or you can try doing multiple clustering and see that maybe after 3 clustering, the separation or the performance does not improve. So you choose k as 3. So after that, you divide the test and training data set. So I did a 8:2 ratio. So 80% of the data was taken for training. And then finally, after you sample from every data set, you merge them. And you have a common training and test data set. Now, I must mention that one of the main problem with this data set for this particular case is that in many papers, people report the major element composition. They do not report the trace element composition. And even if they do report the trace element composition, they often do not give the same sample names. So you cannot put a direct correlation between the trace element and major element composition of the same point. And if you do not have that, you cannot combine the two data sets. So and if you want to combine the data set, your data set becomes too small. So what I tried to do is, as an initial step, I tried to treat them separately. So I ran a different model for major element and a different model for trace element. So what we can see is these are the different type of scans. And for the major element, the support vector machine, it gives a 68% of accuracy. And support, okay, this is KNN, sorry, there's been a mistake. So it is K nearest neighbor classifier. So K nearest neighbor classification, that gives the 80% accuracy for the major element composition. So in that case, what we see is they do not perform very bad. It's not very good, of course, but it's not very bad. So it might be promising. So if we do that for a random forest classification, the accuracy increases to 83%. And as I mentioned that for these kind of machine learning algorithms, you can get a feature importance graph at the end. So you can plot them, what are the feature importance of different elements, and you can know which elements actually help in prediction. So now when I tried the same for the trace element, the accuracy actually is higher for trace element. So in case of SVM, the accuracy increased to 85%. In case of K nearest neighbor, it's 90%. And for random forest, it actually increases to 95% almost. So that shows that trace elements in garnet, they can be a very good indicator of the O-type association. And of course, I think it can be a very good indicator of mineralized, you can assess the mineralized potential of the area as well, or if there is a ore association nearby. So it is very important to look into that. The main, what I would like to mention as a drawback, or not as a drawback, it's an ongoing research, is that the data set that I did this model was this was mainly done in 2020, like till the early 2022 or like 2021. So after that, a large number of publications have come up on scan garnets, and most even even if you look at the papers like the Chinese publications, they have come with a huge number of scan garnet data. So if they are combined, then the data set will increase. And recently, the trace elements are measured. Like the trace elements will be measured in recent publications, so it is very common now. So therefore, the database will become much stronger and like big. And therefore, if these models are run on a refined data, that will be better. And maybe we can try to combine the trace elements and major element as well. And also, I think it might be helpful if we can combine some of these different garnets, and we can reduce the different like the clusters, or so that we can try different methods and we can see how the performance increases. So I would say this part is an ongoing research. And so the earlier part, like till I performed the principal component analysis, that work has been published in 2022. And the supervised machine learning part is an ongoing research, because I think more work needs to be done. It has been submitted as a conference publication, but proper journal publication would require more work on it. And so I would like to thank the IIRES team for inviting me in this presentation. And I would like to thank my PhD supervisor, Professor Devashish Upadhyay, for encouraging me to work on this a different angle in my PhD. And I would like to thank my mentor, Dr. Zhang Zhao, because he had guided me a lot of machine learning help. And I would like to thank Professor Steve Hiller and all members of the James Hutton Institute's recruitment committee who had given me this opportunity to work as a digital mineralogist. And I am excited to learn very new stuff. And so as a concluding remarks, I would think that people a person who is starting with machine learning in geochemistry, they would have these kind of questions. So how much time do we need to do this, because it's an entirely different thing which one might not have been doing till now. So how difficult are learning the tools, what softwares to use, how to start, and what kind of computation power you might be requiring. So I'll try to give a little idea. So time, so it would it depends, because of course you don't need to learn everything, because we do not work as a programmer or a statistician, but the basic tools you need to learn, the basic algorithms you need to learn, because you need to know when to apply which algorithm and how to apply. So a basic understanding of the software programs is required, and because you need to change the models when it's required. So a basic understanding will be required. So it is not very difficult, but you have to put your efforts in. So every new learning requires some effort. So you will be needing some effort. So how to start? You can start initial, if you want to learn the course of the programming, you will find enough material online. If you want to learn the basic mathematical part or statistical part of machine learning, there are several materials online. So you can start with those. Then you have to get your hands dirty, because the data set you would be practicing on, in these cases, they are filtered, they are cleaned, they are ready to use. But when you're working on an actual problem, the data will need work, the data cleaning will need work, organizing the data will need work. So that you can only know when you have when you are doing it practically, and when you are dealing with the data, the geological data. Now, computation power, initially it would not require much, normal laptops will do. But for example, if you are running with a huge amount of data, or it's a complicated problem, the requirement will increase. For example, in for the problem I showed, that's simple, that would not require much. But currently, what I'm working on now, so that requires a cluster or high performance computing. So that will depend on what your problem is. So I would thank you everyone for patiently listening to me. And any questions, I'll be happy to answer. Thank you.
Thank you, Urmi. It was a very nice presentation. The first thing I would like to suggest you that please take a breath. Meanwhile, let us exchange a couple of
Yeah.
sentences with the participants. And on the participants, thank you once again for being there. If you have any doubts or questions, please keep typing in the uh, Google Meet chat box or in YouTube Live chat box. Obviously, the presentation was very nice, and more than induced, I am surprised. I should say that, because as far as I know that our mainstream curriculum, they are not into that machine learning courses right now. Okay, there are not much that structured courses of machine learning we find every day in our courses, be it BSc, MSc, or in the advanced PSc courseworks also. So from that point of view, what you have done, it is certainly a commendable job. So my questions were during your presentation. I had few questions in my mind. Okay, before going to the questions of the participants, I'd like to clear my doubts at first. Uh, so I'm just taking the privilege of being the host. So my questions are mostly related to this learning the machine learning part. Okay,
Yeah.
so as I have just mentioned that our curriculum is not having this kind of structured courses yet. So my first curiosity is that how did you learn this machine learning thing, and what kind of motivations you had at each which point of time in your research you decided that okay, machine learning is the thing people are doing throughout the globe and I can incorporate that in my research, and what was your pathway? How did you learn it?
So initially, when I was working on my PhD problem, so of course we would read a large number of papers, and the common term that came up often is the principal component analysis. So
Okay.
people in case in old geology, I in one or two papers I learned about PCA, and
Okay.
I felt this was something I could use, like in my research I could use, but obviously because I was involved in like regular day to day activities, like I was working like on my current problem, I did not get the time to learn. So what happened was COVID. So during COVID, actually, we were stuck in the IIT Kharagpur hostels, and we used to play guitar and stuff at the evening. So then one of the students from a different department, she said that because on my whiteboard PCA was written as something I want to learn in future. So she said that
Okay.
do you want to learn PCA? So yes, I said yeah, I think because people are doing that, so I want to learn it sometime. So she said even she is like she actually worked with the image recognition. So she said she is also working on it. So she would be interested in learning Python and machine learning together. So that is how we started. Like there were another like one of my junior together with us. So three of us we started learning it together, and that was the first idea. That was the first. What do I say? That was my induction into machine learning and like, this world. But after a while, I understood that just learning these things would not work. I actually have to apply them on some research problem. And initially, I could not do it on my research because I did not have that kind of oriented problem. So I started downloading the data from GeoRock, working a little on it. So that is how I started. Then after my PhD, I also worked with another group that is working on machine learning. So like you have to get your hands dirty. So first you have to
Okay, nice. So beyond your regular curriculum, you took some time out and you kept learning, and that has taken you to this place. That's certainly a commendable thing.
yeah.
And another thing I would like to know that is more technical actually. So as you know, as you have done your PhD and you have published in reputed journals. Okay. Hello, am I
Yeah,
audible?
yeah, I can hear you.
Yeah. So the thing is that whenever we are trying to learn something during our PhD, especially, the main thing that comes to our mind that how can we incorporate that in our publications? Whatever new techniques we are learning, whatever we are learning, method we are learning. So the one key thing remains in our mind that how can I incorporate it in our publications? And while talking about machine learnings, I have seen that there are two major divisions or two major schools of thoughts. That one school will say that when you are learning something, you start learning it from the base. Okay, you learn the basics, the fundamental mathematics and computations that go beyond the machine learning mask. You at first learn that, then you try to employ that in your research. Another school says that okay, there is no need to learn everything from the scratch. You just try to learn it from the learn it how to use it as a black box, and then you incorporate that in your research. Okay, at least from the geochemist perspective, what is your suggestion? What should we do? And for both kind of thoughts, what would you like to say? Which one is good or bad? Like that.
So I would suggest that just try to learn a little bit of it and work on real life problems, because otherwise only learning the concepts, you'll forget the concepts by the time you actually work on the real set of data. And also if you're working on like even for the programmers, they would say that try to do try to work on actual problems on Kaggle or some other platforms. So it's
Okay.
for every one of them, it's like you have to do practical parallelly with the theory. Like you can start to work on a problem, like just learn the basics, you start to work on a problem, and while you work on a problem, you'll get to learn stuff, and parallelly you can learn new stuff. But I don't think only learning and not working on practical problems will help.
Okay, nice, nice. So I don't consume much of your time before going to the questions of the students, and I have only one piece of curiosity left in my mind. I don't actually want the detailed answer for this question. There could be some technical or official things. So you are currently in a job as digital mineralogist in UK, right? So how much this learning, machine learning actually helped you to get into this job, or whether it played any role in your current position?
Well, actually, yeah, of course, it needed, because I worked on ore geochemistry, and this
Okay.
here I work nothing in ore geochemistry. So this is actually here what my role is as a soil mineralogist. So I deal with the mineralogical like the XRD data of soils. So it doesn't align with my PhD topic at all. So it is
Oh,
only the digital part.
yes.
Yeah, it's only the digital thing, like my experience with machine learning, or with the softwares or a little bit of programming, that is what helped me getting the job. Because otherwise, yeah, that has actually helped very much.
Oh, okay. More than the geological steps, I think the machine learning
Yeah,
part helped you
yeah,
getting into this new position. That's a great thing.
yeah.
Okay.
Because they were actually
So,
looking for someone
okay.
who knew the at least who knew the basics of programming. So yeah.
Okay. That's nice to hear. And I think many of the participants can take a note of this point, that you are learning something beyond your regular curriculum, and that is finally leading to a prestigious position. That certainly, this piece of information will certainly work as motivation for most of our participants, I think. Okay, so now I'll gradually move towards the questions. Okay, let me check. Okay, we have got a few questions here. Starting with question from our participant Sri Bhushan. Uh, the participant writes, very nice talk, Dr. Urmi. Have you come across any literature that use email to distinguish between minerals that commonly occur in both igneous and metamorphic rocks? Do you have any comment on that?
So, like igneous and metamorphic rocks, for example, garnets from igneous or metamorphic rocks. In that case, that would I don't think that would need look, some typical problems require machine learning. For example, people are working like on apatites if they are from a a magmatic source or from igneous source. Like they are,
Okay.
if you know, apatites are mainly precipitated from fluid, but the fluid might be igneous or the fluid might be metamorphic. So to separate that, people are using machine learning. I think work is being done. And scheelite, like scheelite can be from igneous source and metamorphic source as well. So but they are mainly fluid precipitated. So it is like people want to know the source of the fluid. So those problems for Scheelite is also being used to train machine learning algorithms to identify between the fluids of igneous source and metamorphic source. But I'm not sure if that is what you're asking, because otherwise igneous and metamorphic rocks can be identified. But it is mainly normally you can identify it, doesn't require machine learning. It is only if you have doubts or that what is the source. In that case, some minerals are being used. Yeah, like at least I know apatite and scheelite is being used.
Okay. Thanks for the clarification. And one common point for all the participants, if you are asking question and your doubt is not fully cleared, you can just drop a email whenever you wish. And all the other participants who are hesitant to write the questions straight away here, they can also come up with their suggestions or queries anytime. Just drop us an email and we'll get into touch with Urmi with your suggestions and comments. Okay, moving towards the next question. The next participant, Shabana Ibrahim. The participant is asking, ma'am, how do the apply machine learning in planetary hyperspectral studies, prism of Mars to be precise for mineral identification? Do you have any comments on this?
I have no idea about the planetary hyperspectral studies, so I can tell a little from the mineralogy perspective that I am working on. So here I am working on XRD data sets to identify minerals.
Okay.
You have to quantify what is the concentration of different minerals in a soil data. So that you can here actually we are trying to use that. So this is we use there is a software, if you can look up. So it is basically POWDR. So I can write. So this is here, this is a R script. So it runs on R Shiny. So this work was already done when I came here. So my predecessor has already worked on it. So this software actually helps to identify the different minerals from an XRD data set. But I am not sure of how you will work that in hyperspectral data from planetary sources. I have no idea. But after you have the you can train machine learning algorithms on that data to do different stuff depending on how large you have a database. But planetary, people working on actually planetary problems will have a better idea.
Okay. Thanks for the clarification. And while talking about softwares, we have one question from YouTube Live. Our participant Riyaj Bhuiya. The participant comments that thank you, Dr. Urmi Ghosh, for this beautiful presentation. This gives me a new window to analyze my data. I am very much curious to know the software you have used. Do I have to learn programming?
A little bit, machine learning. If you Google exact algorithm you want to use, you'll get different web pages that already has those algorithms. There are several people write on different platforms like Medium. So they share their codes, and there are GitHub, Stack Overflow. So there are different resources where you'll get your codes. But you'll have to learn a little bit, because you cannot use every code directly. You have to modify them according to your data. You have to add you have to combine different codes, you have to modify them. So yeah, a little bit of programming is required. I won't say that you have to be a very good programmer, but yeah, of course with time you will be a good programmer. But you'll need a little bit of programming to get started. I think recently for some already there people are coming up with different websites where you have to only feed the data and they'll give you an output. So but I haven't used any of them. So Orange is one, I think, one of them. So you can search Orange. I think there are some websites that is giving that facility, but I haven't used that, because that that takes away your freedom. You cannot modify codes according to your will. So you can only do what you are you are already predefined. So only you can use that. But if you want to modify the code and have some amount of freedom, you need to learn a little bit of programming.
Okay, nice. Thanks for the clarification. Now we are moving to our next question. And considering the time, hopefully this would be the last question for the day, if I'm not wrong. So our participant Imad Yasin, Imad is asking that how can MLA be used to investigate the mineralogy and alteration history of rocks in different geological settings, such as hydrothermal systems, impact craters, or volcanic environments. And Imad has another part of question also, where Imad is writing, how can MLE be used to understand the relationship between mineralogy, texture, and geochemistry in sedimentary rocks, such as shale or sandstone, and how does this relate to the depositional environment and diagenetic history of the rocks?
So this is actually a huge, like broad, like this is
Obviously, yeah.
yeah, it's a subject in itself. So I don't. You have to pick up one problem that can be solved by machine learning. So it's not that I take the machine learning tool and you're like where I can use it. So while you're doing your research, you'll come across places where you feel that this cannot be solved by a conventional tool. For example, as I mentioned, that in many geological problems, you cannot identify if a particular mineral is formed from a hydrothermal source or an igneous source, like a metamorphic source or an igneous fluid. So I'll just explain in detail what I'm trying to say. For example, apatites, they might form when you have a hydrothermal fluid. So when the apatite is precipitating from a hydrothermal fluid, it will leave you'll know that it is a hydrothermal apatite by its texture and all. But you won't know if the source fluid is igneous fluid or it's a metamorphic fluid. So that can be understood by the composition of the apatite or the trace elements in apatite. So, you now you might feel that maybe this can be identified. So I need to combine a database, a worldwide apatite database, and I need to classify where it is very evident that these are from metamorphic sources, these are from igneous sources. They are very evident. So you label those apatites according to their sources. And now, where you are having a confusion with your sample, you treat that as an unknown. So, after you have created a model, you try to run your model, and then you expect an output that the model will tell you your appetites are from metamorphic fluid or from hydrothermal, like igneous fluid. So these are the kind of problems you expect to find. For example, alteration history of rock. There you can look like if the fluid is coming from a hydrothermal source or an igneous source. For example, in case of impact crater, I'm not sure. Some mineral changes or like compositional changes might occur. So initially, you have to create a database, worldwide database, or if not a worldwide database, a large amount of database where the problem is very like defined. Then you can try it for your particular database, or you can try a like unsupervised one. But you have to build a problem, like a solid problem, and you have to back it up. Why machine learning is required? So it is difficult to say like in this huge domain how you can apply. I would say like in sedimentary rocks, I have no expertise in sedimentary rocks. So maybe you can search, like give the topics online and search them, use machine learning, like give machine learning sedimentology, and the journals will come up. So you can have an idea how people are working on it. But like that is not my domain of expertise, so I have no idea.
Thanks for the detailed clarification, Urmi. And we are on the final question now, where our participants are asking directly about the which software to start with. For example, one participant, Fulmati Ram, is asking which one would you suggest to start with, R software or Python? Which one would be good to start, keeping in mind applications in the future? And in the same line, Niraj is asking again, can you suggest a software or any particular platform where I can start my initial learning? So, what is your suggestion on that?
So I had basically started with Python, but now I have shifted to R because my current job profile requires R. So I felt that it's like R is a simpler tool because R is designed for like R is designed for scientists who are trying to do machine learning, whereas Python is designed for programmers. So R I think R is a little bit simpler because and also if you want to plot PCA, the codes are simpler and the plots are more. I like the plots in R. So even when I was working on Python, I did my PCA plots on R because the statistical statistical commands or statistical outputs, or if you're dealing with like data or you're trying to do statistics, I think it is a little better to start with R. And Python is if you're trying to if you want to do hardcore programming, or Python also has like a lot of machine learning algorithms. But I think like after using both, I think maybe you can start with R. You can actually do both, but maybe you can start with R.
Oh, nice. Thanks. Thank you again, Urmi. Uh, it was obviously a nice presentation, and more than that, this discussion session was very much enlightening. And I have rarely been to such presentations where I get information and motivation at the same time. I think all the participants should agree on this point with me. So, without delaying further, I am now going to hand over the stage to Priyabrata. So I think you are there. Priyabrata, are you there?
Hi.
Yes.
Yeah.
Yes.
Thanks. It's a beautiful session, actually. I thoroughly enjoyed this. It's new to me. However, I'm a sedimentologist, but I have no idea about machine learning application in sedimentology. So I just keep quiet at the time. So it's a beautiful presentation with me. So for the IREES side, I have some thing to say more. We are going to start a student volunteer program. So the student those are interested to associate with IIREES can directly apply to our courses, our this program. So it will be like for say 6 month or 1 year kind of tenure. Who are interested to join to work with IIREES, IIREES mentor on different topics in for say research topic or some outreach activities and different other activities related to geoscience and natural sciences can submit your registration. You just go to our social media pages in LinkedIn or in Facebook. We have posted that form. Just fill it up and send it to me, or we will scrutiny we review that thing and we'll call you. So that's all. I think it's very nice, Urmi, and I think in future Urmi may try to build some course material because people are already interested. I know in YouTube the people are watching this thing. In future also they will watch. So we want more for you. Actually, it's a just creating a new thing in India. Thanks for your lecture.
Thank you for inviting. Yeah.
So thanks everyone for wonderful talk, wonderful thing, and so that's all. Naran, shall I close it?
Yeah. I think it was a nice session, and
Yes.
students will go through the recorded video in YouTube if they
Yeah.
want future reference. And as I mentioned previously, whenever you have some suggestions or doubts or any remarks, please feel free to write to us. And with this, we can conclude today's session.
And one more thing that for that registration form that just now we have
Yeah.
circulated in the chat box, just fill it up, and we are trying to provide certificate within half an hour. So we will not take
Okay.
any more attendance after half an hour. Okay, so within half an hour, you just fill it up and send it to it.
Thanks,
Thanks.
everyone. Thank you, everyone.
Thanks.
Thank you, sir. Thank you, ma'am.